The most important variable in evolutionary success over time is not the mutation rate, nor the relative success of each mutation, nor the environment. It is time itself. Life is in part defined by its adaptability. Life finds a way. But it takes time. It always takes time. If evolution were perfect, where every successive generation is perfectly adapted to the environment they are born into, the entire human species could nevertheless go extinct if Earth's oxygen content were erased. And nature is far from perfect. We exist because of the universe's longest-running game of trial and error. Remove just 1,000,000 years from that timeline, and we cease to be. If successive adaptive generations cannot be reproduced faster than the environment itself changes, a species is doomed. Damned by the environment, damned by the world, damned even by us. Damned by time. They just weren't given enough of it. How long do you suppose we have given them?
We do not know where the carbon dioxide is coming from. There are several possibilities still in play, from solar cycles to precession cycles to increased geothermal activity. Whatever the case may be, we know that the concentrations are rapidly increasing, and that there is zero indication across all our measurements hitherto discussed of its decline. We must look into the future, therefore, as though it will keep rising. We are by now intimately familiar with two direct consequences of this trend: increasing atmospheric temperatures and increasing oceanic acidity. In the last act, I ended by making a few cursory predictions into the second-order effects, the consequences of rising temperatures and lowering pH. From there, we may even look to third-order consequences or higher, as necessary to understand the true impact of these global changes. Have you seen a sea butterfly before? Ephemeral and gorgeous, they flutter in the dark Arctic waters. What kinds of stories would they tell? What would they want to share with us? Whatever it may be, their voices may soon fade. Their shells are dissolving. They are mollusks, and create their protective homes with calcium carbonate. Now they're dissolving. A shell in isolation will dissolve very rapidly with only a small increase in acidity, a level of acidity we're likely to reach based on current projections. Coral reefs rely on calcium carbonate, and as we know, an acidifying ocean removes more and more of it from supply. Mollusks require it too, echinoderms such as starfish, sand dollars, and sea cucumbers. Crustaceans use it for their outer shells. Foraminifera, which we know well by now. Even phytoplankton. Thousands of species of animals across the entire oceanic ecosystem require calcium carbonate. What happens when you reduce the amount available? Stretch it thin, make them compete more and more. Make their shells weaker and weaker. Some animals are far more resilient than others, or even just across their lifespan. Often they can find replacements in the composition of their shell. This isn't easy. The reason so many organisms utilize calcium carbonate for this purpose is precisely that it is the most energy efficient option available to them. Utilizing any replacement will be more demanding. That means each organism will have less energy available to hunt for food, less energy to defend, less energy to reproduce. On an individual scale, this may be insignificant, a footnote at best. On the scale of an entire species, or on thousands, tens of thousands of species across the planet and across the food chain, suddenly populations start to decrease. Pure statistics dictate so. Based on the current rates of ocean acidification, it is projected that by 2080, average conditions will be such that coral reefs globally will be dissolving faster than they can build, due to a combination of the calcium carbonate shortage and the destruction of their current skeletons from the acid in the waters. These are not idle hypotheses either. We can directly go out and measure the coral reefs. We have found a steady decline in coverage. Not all coral species are so affected or to the same degree, but enough are that there will be massive changes. Psst! Hey, do you want to know something cool? The average pH level in human blood is 7.4, or very slightly basic. Normal variation is between 7.45 and 7.35. blood pH below 6.8 is almost always fatal. But it need not be so severe. Acidosis starts below 7.35. The clinical presentation of respiratory acidosis is usually a manifestation of its underlying cause. Signs and symptoms vary based on the length, severity, and progression of the disorder. Patients can present with dyspnea, anxiety, wheezing, and sleep disturbances. In some cases, patients may present with cyanosis due to hypoxemia. If the respiratory acidosis is severe and accompanied by prolonged hypoventilation, the patient may have additional symptoms such as altered mental status, myoclonus, and possibly even seizures. Respiratory acidosis leads to hypercapnia, which induces cerebral vasodilation. If severe enough, increased intracranial pressure and papilledema may ensue, increasing the risk of herniation and possibly even death. Cases of chronic respiratory acidosis may cause memory loss, impaired coordination, polysthenia, pulmonary hypertension, and heart failure. Persistence of apnea during sleep can lead to daytime somnolence and headaches. In patients with an obvious source of respiratory acidosis, the offending agent needs to be removed or reversed. pH is very important. Small changes can be very dangerous. It could be pointed out, and rightfully so, that a lot of these problems are because carbon dioxide is replacing oxygen in the blood. What do you think happens in the waters of the ocean? Fish can also experience acidosis. Their primary source of water is, surprise, seawater. As the acidity in seawater rises, so too would the acidity in their blood. From there, two things can result. Either the fish suffers the negative effects of acidosis, or their body must expend significantly more energy to maintain homeostasis and rid themselves of the acid. Yet still, there are many other important physiological effects that fish species globally may experience. This includes, and of course varies by species and location, effects on hearing, smell, behavioral patterns, how they react to both predators and prey, the ability to learn, vision, growth, development, their DNA and RNA, tissue damage, lipid content, reproductive behavior, the offspring of that reproduction, oxygen intake, mitochondrial respiration, enzyme behavior, gene expression, membrane structures, ventilation, etc. Just as with corals, not all fish are affected as expressed. Some may even thrive, but the entire food web would be radically altered with unknowable alterations therefrom. General principles, however, still apply, such that if there is a significant decline in smaller organisms, the shellfish, the plankton, the crustaceans, etc., that we know are majorly negatively affected, their predators will find themselves with much less food, and so on. Or if the most biodiverse part of the ecosystem, coral reefs, on whom 25% of all marine life are dependent, suddenly starts to shrink, or become unhealthy, or die off, that's going to be a major upset and lead to a lot of issues for the dependent species. Inevitably, it comes back to us as well. Have you ever wondered why hurricanes don't form in the North Atlantic or ever hit Antarctica? The answer is heat. Hurricane formation, sustainability, and strength are all dependent on heat. Specifically, a hurricane requires warm ocean water, warm and humid air, low air pressure, and low wind shear. The more potent these variables are, the stronger the storm is. The longer the storm is in contact with these appropriate conditions, the stronger it becomes. We expect, therefore, that as temperatures rise, hurricanes would become stronger on average. A warmer atmosphere creates a warmer ocean and makes moisture intake into the air easier as well, fueling the storm. And on small scales, this is precisely what we have seen. Unfortunately, longer-term data is not available, but so long as the trends of warming temperatures continue, and we have no reason to suspect it won't, so too will the strengthening of the storms. Specifically, between 2019 and 2023, 80% of Atlantic Basin hurricanes were intensified due to warmer temperatures, with wind speeds on average 18 miles per hour faster than if the temperatures had not warmed as they have. All hurricanes from the Atlantic Basin in 2024 were intensified. Moreover, we would also expect hurricane formation, and all the previous steps thereof, to become more frequent. Hurricane formation is exceedingly particular. All four conditions must be met at the same time and in the same place for a storm to ever progress this far. However, as average air and ocean temperatures increase, the viable range for formation expands away from the equator. It is important to note that we do not have yet explicit or solid evidence of such trend, but this is an expected result given the small scale of our records. This is an open-ended issue. Just as rising atmospheric temperatures increase its capacity to evaporate moisture over the ocean, so too does it evaporate more moisture over the land. We can expect two co-occurring effects from this phenomenon. The effects on evaporation are likely to be uniform. However, the effects of evaporation are already disparate across regions. For many reasons, such as mountain ranges, jet streams, depressions, ocean proximity, and more, some regions experience droughts and others experience floods. Both would, in theory, be exacerbated by rising temps. In a region prone to droughts, even more moisture would be taken from the air, and whatever increased moisture would reach it is already being blocked. Meanwhile, regions prone to flooding or high levels of precipitation generally would get even more, as there would simply be more moisture to become precipitation, and nothing stopping it from reaching its destination. This is a very difficult pattern to measure and record. Weather, of course, is highly variable, and smoothing it out over such relatively short periods for which we have accurate measurements is not so effective, made worse that most countries simply do not have and cannot attain accurate data all the time, and moreover especially don't have data going back centuries. For these reasons, much attention will be had on precipitation records globally moving forward. Fortunately, the United States does have such records. The share of land in the United States that experiences unusually high amounts of precipitation, that is, higher than expected given historical data, has been increasing for the past 2 decades. Similarly, there is an increase in extreme one-day precipitation events. Droughts do not share such a trend, but this is largely expected when considering the geography of the US. Fortunately, there are other resources available for droughts. Their own words shall do justice. Drought is one of the most common and complex natural hazards affecting the environment, economies, and populations globally. However, there are significant uncertainties in global drought trends and a limited understanding of the extent to which a key driver, atmospheric evaporative demand, AED, impacts the recent evolution of the magnitude, frequency, duration, and areal extent of droughts. Here, by developing an ensemble of high-resolution global drought datasets for 1901 to 2022, we find an increasing trend in drought severity worldwide. Our findings suggest that AED has increased drought severity by an average of 40% globally. Not only are typically dry regions becoming drier, but also wet areas are experiencing drying trends. During the past 5 years, 2018 to 2022, the areas in drought have expanded by 74% on average compared with 1981 to 2017, with AED contributing to 58% of this increase. The year 2022 was record-breaking, with 30% of the global land area affected by moderate and extreme droughts, 42% of which was attributed to increased AED. Our findings indicate that AED has an increasingly important role in driving severe droughts, and that this tendency will likely continue under future warming scenarios. Moreover, this same twin phenomenon, where areas with little precipitation have even less moisture, and those with plenty get flooded, has 2 other consequences for each side. On the one hand, dry regions that tend to be prone to wildfires can expect those wildfires to get significantly worse, both from less moisture and also from greater ambient temperatures. On the other hand, increased precipitation will extend into the winter months, meaning more snowfall in shorter periods of time, which anyone who lives under the tyranny of the snow will know is very dangerous. That is a prediction we can make despite another prediction, that winters will be warmer and shorter than average. If temperatures are rising, we expect this to be matched across all 4 seasons. And lo, across 235 locations in the United States, from 1970 to 2024, winters have warmed 4 degrees Fahrenheit on average. That is in 98% of locations measured out of 241. Would you believe it, but the warming was the worst where the winter is usually the most severe, like right here in the upper Midwest, including in my own county, where I live, where all of my family lives. That's scary. I've been narrating this largely as an impersonal piece. I believe my emotional emphasis has come through at least somewhat well, but I'm still treating it like a narration all the same. A story, a project. But it's intensely personal. It has been intensely personal this whole time. I live in a tourist town on the lake. I'm extremely fortunate that I'm not in fear of the coast or the storms.
but I do still see the effects directly. Year after year, I hear laments that the lake just ain't as cold as normal, that ice fishing season just isn't it this year, and suddenly people pack up and leave, and suddenly the old tourist town ain't getting tourists no more. And hell, man, I'm writing this, I'm making this, researching all of this for my mom. She's the denier. She's the person I'm preempting. She's the person I'm doing my absolute damnedest to reach out to. I'm trying to answer every question she specifically has, to counter every single regress she specifically gave me. Because this matters, right? This matters. We all live here. And it's absolutely terrifying that there's nothing I can do. I sit here and I write and I record and I pretend I'm doing something. I tell myself that if I could just reach this one person, I will have contributed. Change just one person's mind. That I'm doing my part. It's easy to understand and cognize that there is an existential threat to humanity, right? It's harder to understand that there's an existential threat to my family, to my friends, to my home, to my community. How selfish of me. But it's true, and when I come to face this nature of the beast, I suddenly feel as though I'm wasting what productive time I have on things that don't matter. I'm not so arrogant as to think that I could save them from anything to come, but maybe I could join that effort more directly and not sit here. And then I want to stop writing this altogether because it doesn't matter. Because it won't do anything. It won't solve any problem. And then I get back to writing. Because the only way to reach a million people is to reach one person a million times.
On the one hand, forest fires are getting more frequent and more severe. Quote, extreme regional fire years generally coincided with exceptional or record high fire weather, quantified by the Fire Weather Index, FWI, calculated from the Canadian Forest Fire Danger Rating System, for our case study regions. Notably, FWI metrics including the number of days per year above the 95th percentile, the maximum 90-day moving average FWI, and the annual maximum FWI were at their highest values during the 1979 to 2023 period for extreme fire years in the western US in 2020, Canada in 2023, Southeast Australia in 2019 to 20, Chile in 2022 to 2023, and Siberia in 2012. All case study regions except the Amazon and Southeast Asia regions had FWI metrics exceeding the 1 in 15 return period during the record fire year, codified with a generalized extreme value approach using data from a 1979 to 2023 baseline, suggestive of the role of climate variability in enabling and driving extreme fire years. While extreme fire years in the Amazon and Southeast Asia regions occurred with moderate FWI and drought, these years were strongly influenced by deforestation and land clearing fires, which occurred earlier in the study period and have waned over the past couple decades. Using data from researchers at the University of Maryland, recently updated to cover the years 2001 to 2024, we calculated that forest fires now burn more than twice as much tree cover each year as they did 2 decades ago. This increase in fire activity has been starkly visible in recent years. Record-setting blazes are becoming the norm, with 4 of the 5 worst years for global forest fires occurring since 2020. 2024 was the most extreme year for forest fires on record, with at least 13.5 million hectares of forest burn, an area roughly the size of Greece. This surpassed the previous record of 11.9 million hectares, set in 2023, by about 13%. And some estimates suggest the true toll of 2024's fires may have been even higher. There was an overall 8-fold increase in annual area burned at high severity across all western US forests. The relationships identified between the annual fire severity metrics and climate, as well as the observed and projected trend toward warmer and drier fire seasons, suggest that climate change will contribute to increased fire severity in future decades. All as predicted. And on the other hand, we're already seeing increased lake effect snowfall around the Great Lakes, attributable only to increased evaporation. We're not quite done with winter. Everything around us is stupidly complex. Whatever device you're consuming this content with might as well run on ones and zeros and... oh, bad example. Fathoming the interactions of the entire atmosphere is a pipe dream. Even on the scale of continents or quasi-continent scales, there's a lot of complexity to it. A warming average temperature would never tell us the full picture. The polar vortex is a mass of cold, low-pressure air that exists above the poles of the Earth. It is a rotating mass, and on the edges of it, where it meets the much warmer, higher pressure air, there forms what we call the jet stream, a relatively thin but incredibly fast-moving stream of air tens of thousands of feet above. The polar vortex is generally the largest and strongest in the winter, and vice versa in the summer, where the difference between the cold and the warm sides are less pronounced. This also weakens the associated jets. Even outside of seasonal recrudescence, the border is inconstant. Every now and again, the jet stream will move south, and normally mild, or at least milder locations, will suddenly be hit with a gust of that sweet, sweet Arctic air. The entire vortex can even be split in two, which is awesome in the literal sense. This sort of shifting of the border is exactly what we experienced in early 2019. To my Americans and Canadians, you probably remember this well, no matter what part of the respective country you reside in. There were decade-long records broken across the continent. Freezing temps reached as far south as Texas, though they escaped the vortex itself. Winnipeg in Manitoba reached temperatures of -40 degrees Fahrenheit, or -40 degrees Celsius. Not a typo, they crossed at -40, really cool. In Minnesota, a town near Duluth reached -56 degrees Fahrenheit, -49 C. Wind chill elsewhere brought the temperatures down to -66 Fahrenheit, -54 C. Los Angeles, for all of February, never managed a temperature above 70 degrees Fahrenheit, 21 Celsius, something never before recorded in 142 years. And this sort of structure is happening right now as I'm making this, actually. It is -20 degrees outside, wind chill down to -40. And the entire country has been preparing for this for weeks now. The jet stream weakens in the summer, specifically because it is given momentum by the temperature difference on its sides. A warming Arctic, therefore, lessens the momentum, and the entire stream is more likely to bend and shift in response to local atmospheric disturbances. A weaker jet stream is more likely to go south. It is thus more likely that we will experience an event such as what struck in 2019, or is happening now to an even milder degree, given the known fact of warming atmospheric temperatures, especially over the Arctic. So, winter is going to look very weird for a while. It will be incredibly locally intense, with brief moments of massive freezes and storms that bring in feet and feet of snowfall, but will be overall milder and shorter. It will be erratic. It will be erratic because we live in a complex world, and a change to a single variable, such as temperature, can result in multiple unexpected consequences. Unexpected until you understand that the world, however complex, still operates on the same rules. Do you know what else happens when a normally cold area starts to warm up? Ice melts. Between 2002 and 2023, Antarctica lost an average of 147 gigatons of ice annually, or a total of 3,087 gigatons, or 3,087,000,000,000 tons. Not just pounds, but tons, metric tons even, which are 10% heavier than imperial tons, of ice in 21 years. It is an extremely popular point among specific ideologues to point out that the ice sheet is growing on the eastern quarter. This is true. Or it may be pointed out that on a year-by-year basis or month-by-month basis, there are times of shrinking and times of growing. This is also true. But they are not the whole picture, and it is deeply unfortunate that many have uncritically accepted such framing. The eastern quarter grows due to the increased evaporation of water driven by warming atmospheric temperatures, and moreover is significantly below the loss in other regions. Similarly, although the ice grows in the winter months, and occasionally grows enough to offset yearly losses, those losses are much, much greater than the gains, and the trend line points ever downward. Greenland, too, has lost ice. More ice. Between 2002 and 2025, the Greenland ice sheet lost an average of 264 gigatons annually. This is 6,072 gigatons, or 6,072,000,000,000 metric tons of ice. Given that we expect temperatures to continue to rise, we therefore expect ice to continue to melt. But meltwater has to go somewhere. Perhaps, just perhaps, it may run into the large body of water that surrounds and often underlays these ice sheets. You know, the ocean. Let's do some really quick math here. We're going to try and find a rough estimate for how much we would expect sea levels to rise given this level of meltwater. It won't be perfect. There's a huge amount of variables that will give even hardened researchers pause, from calculating the amount of water melted from other glacial bodies globally to the increased atmospheric evaporative demand, to the fact that every small increase needs just slightly more water than the last to raise by the same amount, that ice is of a different density than water, and much more. But we can get close. If our answer is off recorded numbers by a whole digit place, then we can confidently say that something is going wrong. But if we're within a reasonable distance, then that offers significant credibility and parsimony. We are working with 9,159 gigatons of ice. Fortunately, metric is kind to us, and the weight of a kilogram is already determined by the standard weight of water. A single metric ton is 1 cubic meter of water. Therefore, this is roughly 9,159,000,000,000 cubic meters of water. The surface area of the oceans comes to about 361 million square kilometers. There are 10 billion square centimeters in a square kilometer, so to raise the surface by just 1 single centimeter, we would need, this is a big number here, 3,610 quadrillion cubic centimeters. In a cubic meter, there are 1 million cubic centimeters, for a total of this number. Dividing those numbers gets us a whopping 2.5 centimeters. From 2002 to now, we've recorded a roughly 7 centimeter rise in sea level. This is done through using satellites on a fixed, angled orbit around the Earth such that they slowly glide north and south over the surface, and then return to the same path every 91 days, 4 times a year. These satellites fire a laser down to the surface every 170 meters and record the time it takes for it to return. Based on the speed of light, we can therefore measure the distance from the ground to the satellite with extreme precision. More importantly, since its orbit is cyclical, we can measure change over time. This is the same method we use in large part to measure changes in the ice sheets. We are in the same order of magnitude, which is an excellent sign. With that, we can look at the larger contributing factors. Of all the variables at play in rising sea levels, it's estimated that Arctic and Antarctic melting is only responsible for 23% of it. Absolutely stunningly, we can make use of incredibly vanishingly micro adjustments in Earth's gravitational field as mass moves from ice to water to estimate the amount. Science is the coolest thing ever. Unlike our ice caps, heyo! Yeah, this is actually a really, really bad. 177% of 2.5, the remaining 77% of variables plus 1 because math, is 4.425. Add them together for the full 100%, and would you look at that? It's 6.925, 7 centimeters. Let's take a look at those other variables. Land ice, overwhelmingly to the point of near absolution being mountain glaciers, represent 21% of the rising levels. Despite their minuscule size compared to the ice sheets, they are, for that very reason, far more susceptible to changes in temperature and are thus more vulnerable to melting. Their losses have matched Greenland's and at times surpassed it. However, this effect will diminish as there will simply not be much left to melt. The plurality of the rise is actually from warming. Warmer water has a greater volume than colder water. We have already established that the water is warmer. We have studied water to a great extent and know incredibly precisely how much it expands under different conditions, especially temperature. In measuring the temperature at various depths, using a variety of technologies like buoys and aquatic drones, we can calculate the expected expansion. When we do that and then add it to the calculations derived from meltwater, we receive an outcome near perfect to what the satellites are literally actually recording across the globe. We have been using this satellite technique since 1992. but we've also used tide gauges, which measure local sea level compared to the land next to it. Doing this again and again, and we can find the trend line. Normally, they are used to measure differences between the tides, but some gauge records go back 100 years or more. These are especially important for local communities as sea level changes do not take place uniformly. Many factors, like the major currents, can make a given area rise more than average and another less. Importantly, there is still a global rising. From these tide gauge records, we can say that since 1920, the sea has risen 6 to 8 inches, or 15 to 20 centimeters. The time since 1992 alone accounted for 10 of those centimeters. The rising is accelerating, just as the temperature is, just as the CO2 levels are, just as the ocean acidity is, just as the ice melting is. They all corroborate each other. Tangai Island, off the coast of Sierra Leone, was 700 meters in length in the first years of the 2010s, consisting of low, sandy beaches and covered in forest, complete with a population of around 4,000 throughout 50 homes in 3 different villages. Now, a decade later, it's 100 meters long and less than 100 wide, with a population only in the hundreds. The forest drowned and the land submerged. Days of flooding during high tide increased by 400% in the U.S. Southeast Atlantic coast, and 1,100% in the Gulf Coast from 2000 to now. Across the entire United States, high tide flooding is twice as frequent. Flood walls that withstood the tide for hundreds of years are now overwhelmed. This is exactly what we should expect to see given rising sea levels, and indeed can only be explained by rising sea levels. The only other possibility is that somehow tidal forces are themselves growing stronger over the span of 2 decades, with literally no other observable side effect, and no evidence. Over the next few decades, the level will continue to rise as per all our measurements that have zero indication of slowing down. Flooding will become more common. It will be a longer time, perhaps on the scale of half a century to century, before significant swaths of land are threatened, but that time, if nothing changes, will come to pass. Everything we are observing, the direct consequences of increased atmospheric CO2, will continue so long as the concentration increases. And all evidence so far gathered tells us it will. As discussed, between 2000 and 2024, the ppm of CO2 in the atmosphere increased by 53.1 parts. Before we reach Act 4 and find out once and for all the source of this increase, I want to use this measurement to roughly determine how much CO2 this really is. Any source that falls short cannot be our culprit in full. Because the atmosphere is a great mixture of an untold amount of particles of dozens of elements and chemicals, though often in just trace amounts, we cannot quickly measure by volume nor density. Fortunately, ppm is easily convertible into percent. CO2 is 0.04228% of the atmosphere. As a decimal, that's 0.0004228. So our difference between now and 24 years ago is 0.0000531 atmospheres. Next, we need to know the mass of the atmosphere altogether, which we know to be 5.1480 times 10 to the 18 kilograms on average. The molar mass of the atmosphere is 28.6 grams per mole. The molar mass of CO2 is 44.0095 grams per mole. With these numbers, we can multiply the concentration of carbon dioxide, 0.00531%, by the molar density of carbon dioxide, 44.0095 grams per mole, and then divide the result by the molar density of air, which is 28.8 grams per mole, to get what percent the atmosphere's mass is CO2. This number is 0.00008171. We can then multiply the mass percentage by the actual mass of the atmosphere, for a total mass of CO2 by 420.64 gigatons put into the atmosphere between 2000 and 2024. To ensure that nothing has gone awry, let's go through the process a few more times. 0.04228% multiplied by the molar mass of carbon dioxide, and that number divided by the molar mass of the atmosphere yields 0.000658. Multiplying by atmospheric mass brings us to 3,397 gigatons. Taking the 2,000 levels of CO2 and running through the same process, we get 2,929 gigatons. The difference between the two is 468, which altogether is exceptionally close given the liberties I've taken both with rounding and significant digits. Moreover, we can run this process again for one single part per million, and it returns 7.9 gigatons. Multiplying this by our different parts per million values, we get 3,340 gigatons in 2024, 2,920 in 2000, and our difference of 53.1 returns 419. These are incredibly close, completely as expected. Again, minor differences come from differences in rounding. For one last important measuring point, the CO2 ppm was stable for a few thousand years, around 280, up until the late 1700s, which we can verify through all the measuring devices already examined. This is our effective baseline, before such events occurred as to increase the concentration. 280 parts per million gives us, in mass, 2,218 gigatons. Checking with our reference of only 1 part per million, we get 2,212 gigatons. So we're looking at a source of CO2 that is, in the past 250 and change years, responsible for 1,185 gigatons, and between 2000 and 2024 alone, 420 gigatons. But this isn't the full scale either. As established, much of the CO2 in the atmosphere goes into what is known as carbon sinks. One notable sink is, of course, the ocean that we've been talking about. In general, the ocean absorbs 30% of atmospheric carbon dioxide. This varies, of course, with temperature, pressure, and concentration itself in both the ocean and the atmosphere, and other variables, but 30% works for our rough purposes here. Other estimates, depending on, from what I can tell, though I'm very well may be mistaken here, whether algae is counted for land or ocean sinks, places the ocean sink at around 20%, and the land sink, which involves the actual physical soil and dirt and rocks and all the plants growing therefrom, at 30%. Whatever the specific differentiation between the two main sinks, roughly 50% of the atmospheric carbon dioxide is being absorbed. That means that our parts per million measurements are half of the total source of CO2. We are actually on the lookout for a source around 2,370 gigatons overall, and 840 gigatons between 2000 and 2024. This source we shall find in the next act. Class dismissed.